All Marines prepare to drop.
Hell, it's about time.
I know, it's been a while since I've recorded my tutorial. This one will be the first in a series covering procedural motion with use of MEL expressions. I will try to replicate jet animation from this Starcraft 2 cinematic, and I will be focusing on mechanical movement. I'm going to assume that you have some experience with Maya's MEL language, and I will focus on one technique that I've been using for over 10 years to achieve a variety of dynamic effects and secondary animations. This is one golden formula that can be tweaked to produce anything from random crowd simulation behavior to facial animation or mechanical interaction. At the heart of this technique is a noise function, and I'm going to need some simple objects to illustrate how it operates. For now, a pair of cubes will do. I'm going to go to Expression Editor, which is accessible either by going through Window, Animation Editor's Expression Editor, where you can select the object and its attribute, or there is even a simpler way to access the same panel by selecting the object and going to one of its attributes and hitting Expressions, and it opens the exact same window. To make the first cube animate, I'm going to copy and paste pcube1.translatex into the work window, and we'll make it equal to noise of time. If I hit create and set the timeline to play, then I will see the object translate along the x-axis. I'm going to make the second cube move in a slightly different fashion. I will copy and paste the same line that's responsible for its translatex attribute. I will rename the object to pcube2, and I will make it equal to noise, but instead of time, I'm going to use frame divided by 24, just to illustrate a point. Even though the expressions differ slightly, both objects animate exactly the same, and that is because each unit of time contains 24 frames of animation. And if we check our playback speed, it's set to 24 frames per second, and it's also in settings in the time attribute. So if I change that attribute to something like NTSC 30 frames per second, you will see that the second cube will jump, and it will animate differently. And if I go through different settings, each one will affect the rate of its animation, while the first cube will remain consistent. For that reason, I always recommend that you use time whenever possible instead of frame, unless the setup requires you to have specific frame-related animation. For now, I will change that attribute of the second cube to time. Next, let's try to figure out how to manipulate the noise function to achieve different animation parameters. Time is related to speed, so if we multiply it by 2, then the obvious result is that the first cube will move twice as fast as the second one. And if we multiply by something smaller, let's say if we cut the time in half by multiplying by 0.5, then you will see that the cube all of a sudden will move at half speed. It will still cover the same distance, but a lot slower. There's another way of doing it, and I will show it on the second cube. If I divide time by 2, then what's going to happen? The second cube is going to be moving at half speed as well. So which is the best way of doing it? My advice is to be using multiplication whenever possible while avoiding division, and that is done for certain situations where you're going to be changing values. Sometimes one of your factors might become 0, and even though multiplying a value by 0 will not create any paradoxes, division by 0 is actually not possible in mathematics, and it will cause Maya to halt. Right now, if you look at it, Maya is throwing division by 0 error. The first cube is able to animate, but the second one is the one that's causing all the problems. Let's restore expressions to their original form and focus on the magnitude, the range of motion. We do that by multiplying the entire formula by a number. If the number is 2, then the range of motion will double. If I change it to 4, then it will quadruple, and you will see that the first cube is moving 4 times as far as the cube on the right. If the value is smaller, then obviously the range of motion will also decrease proportionally. Once again, use multiplication and avoid division whenever possible. All that's left at this point is to clean up all of our factors and take them out so that the expression is easier to process. I'm going to temporarily disable the second cube. I'm going to comment out its expression line, and I will create some variables, some float variables, which will act as multipliers, and will stay at the top of the expression to make everything nice and neat. So the thing that we multiply time with is typically called frequency or speed. I will call the variable $FRQ for frequency. I will make a float variable called frequency, and I will make it equal to 1. So when time is multiplied by 1, it's essentially time, unchanged. Then I will take another multiplier and I'll call it $amp, which is short for amplitude, and I will also make it equal to 1. There's another variable that I'm going to be adding inside the noise expression, the use of which I haven't yet demonstrated. It is called offset, and it's going to allow me to manipulate time in a slightly different fashion. It'll be similar to sliding animation curves left and right in the graph editor. I will type plus $offset, and I will also go to the beginning of the expression and declare that variable, and you will see why it's needed a bit later. I will make it equal to 0 for now. You know what? Even before I do that, I'm going to temporarily enable the second cube and just show you what the offset does and why it's useful. Let's remove the comment tags from the second line and duplicate the expression exactly as it is for the second cube. And instead of having offset as a variable, I will just add a small value to the second, to the place where the second offset would be. And if I hit play, you will see that the second cube is following the first one, but it's slightly delayed, and the delay is based on whatever number that I put in as that offset. So the time for the second cube is delayed by the number of seconds that I specify as offset. So how would you be using that offset in practice? I guess I need a better illustration. Let me disable the second cube and reinsert the offset float variable into the first expression. I think I'm not even going to need the second cube for this. Let me delete the expression and instead animate the X, Y, and Z translations of the first cube, and you will be getting the idea of where I'm heading with this. I'm going to be making myself 3 noise functions. I'm going to take them out of the expression, declare them as floats, and I will call them noise X, noise Y, and noise Z, and they will be connected to translate X, translate Y, and translate Z of the cube. Once again, I temporarily remove the offset variable for illustration purposes. I'm going to make 3 connections from each translate attribute directly to its corresponding noise function. Translate X to noise X, translate Y to noise Y, and translate Z to noise Z. I'm going to hit edit to apply the expression and hit play. And what you're seeing right now is that the cube is moving along all 3 axes in a perfect diagonal. In order to randomize X, Y, and Z animation, we're going to have to add different offsets to each of the attributes. Right now I'm trying a small value, and you can see that the cube is beginning to shift off that diagonal line. It's introducing some randomness into X and Y, even though all 3 are driven by the same expression. If you produce just enough offset, then it will look like each axis is acting independently while being controlled on the inside with the exact same animation curve. In order to control all 3 offsets with one variable, I'm going to add offset times 1, offset times 2, and offset times 3 into each of the translation components. I have to make offset multiplier something other than 0, and you will see that the bigger the value becomes, the more the object begins to drift, and at some point when the value is high enough, it'll look like the object is moving independently along each individual axis. On the inside, we have to remember that it's the same animation curve, but if it separates far enough, then it will look like X, Y, and Z movements are completely detached from each other. And now let's start fresh and get back to the reason behind this tutorial. Let's make ourselves a functioning jet engine controlled with procedural expressions. I will start by modeling a single fin of that jet engine by scaling this cube until it looks roughly like a wedge. I moved its vertices to make sure that the pivot stays at the lower end of the object, and I will name it fin1. I will move it off to one side because I'm going to be replicating it around the radius. And the easiest way to do this is to hit Ctrl G and group the object. That way the pivot of the group will remain at the center of origin and the local pivot of the geo will stay at its base. Now all I have to do is multiply that single jet blade around the center. I will take its group and, well, it's a good idea to rename that as well. I will call it fin group 1, and I will go to duplicate special. I will check the option box, reset all the attributes to default values, and I will be copying the group 35 times around the y-axis, each time shifting it by 10 degrees, which will give me a nice 360 degree circumference. Don't forget to check the last option box, that is very important. That option will give each object inside the group a unique name. Without that option, if you just duplicated the objects manually with Ctrl D, then each group would contain fin1, and that would make it a lot harder to set up the expression in the end. Right now, if we select all the fins and try to change the rotation Z value, then you will see that, well, they will all follow the same local orientation, which is exactly how jet engine operates. This time, instead of animating translation, we will be animating rotation Z. Let's copy and paste fin1.rotate Z and begin constructing the noise expression around it. We will once again create floats for each of the multipliers. Float amplitude equals 1, float frequency equals 1, float offset equals 3. 3 is a good value. I typically recommend using 3 or more for truly randomly looking offsets. I will once again declare noise function as a separate float. I will call it rod z for short, and I'll make it equal to noise of time, just as last time. Time will be multiplied by frequency. Then the entire noise function will be multiplied by amplitude, and the offset is going to be sitting right next to the time function plus offset times 1, and I'm just multiplying it by 1 temporarily just so I can remember to introduce different multipliers. And if I hit edit and hit play, the blade is moving. It doesn't move that far, so I have to multiply the amplitude. 10 will give a range of motion of -10 to +10 degrees, and if it's something greater like 30, then I'll be going from -30 to +30 degrees. Now it's nice and visible, but do we really want to recreate the same expression 36 times for each individual fin? That would be a lot of work. Isn't there a simpler way of achieving the same result? And luckily there is. To prepare the expression, we have to change how the value of rotation is being applied. Instead of making it equal directly to the noise function, we have to use a set attribute command. And that will come in handy when we introduce a for loop into this expression. If I hit apply right now, it doesn't work because I mistakenly left an equal sign in there. It still doesn't work, and that is because the attribute name has to be written as a string, which means it has to be surrounded by double quotes. I fix it by putting double quotes in here, and if I hit edit and play, I will see that one of the blades is animated. Now we introduce a for loop, and the for loop will make that set attribute command run multiple times. We do it by setting an initial condition like this: for open bracket $i equals 1. Then we set the limit, which is $i less or equal than 36, and then we end with an increment, which is $i plus plus. And then we take all of our expressions and put them below the for loop inside squiggly brackets. If I hit edit and play, we will see that we only have one fin operating, and that is because the way that the expression is written right now is that it executes 36 times, but it does it for the same fin. So it receives the same noise value 36 times, and it ends up being exactly where it was initially. To introduce variance, we have to change the expression like this. I is going to be different each time we run through the loop. So if we replace 1 in fin 1 with a $I, then each time the expression runs, it'll get applied to a different fin. And you will see that now all 36 of them are animated with the same expression, but they still don't have any offset. And you know that I value, the increment for the for function, it can be introduced as a multiplier for the offset, and that will be very convenient. So if I copy and paste it in here, then offset each time, each blade will receive a different offset. We hit edit, hit play, and you will see now that every fin now looks like it's receiving a completely different animation. It is still based on the same curve, which is resampled 36 times, and all we have to do to introduce randomness is change the offset value. Once again, I recommend having a value of 3 or greater for offset, because that is the point where the human brain stops noticing correlation and begins treating every animation as unique. For the next step, I'm going to modify my scene and double the number of blades in order to make it look more like the setup from the Starcraft 2 cinematic, where they had a double set of control surfaces. I'm going to group all of my existing blades, and I will name the group as outer ring group, and then I'm going to duplicate it using the same duplicate special command, only this time instead of copying the blades 35 times, I'm going to copy the group only once, and I'm going to scale my result by 0.5 in X and Z axis. I'm going to make the resulting set of surfaces even smaller by scaling them vertically. Then I'm going to locate the group, which currently carries the name of the outer ring duplicate, and I will rename them to inner ring group. Next, I'm going to modify the expression. Right now we have a total of 72 geometric objects, but since all of them still carry the same base name of fin followed by an index, in order to expand our animation to the entire set of objects, we just have to change the limit from 36 to 72 and hit edit. And if we hit play, we will see that the animation has now expanded to the entire set of objects in the scene. We now have 72 jet blades that are animated individually, and we haven't even set a single keyframe yet. And let's just zoom in on the expression. See how little work it actually takes to animate nearly an infinite number of objects. Imagine how much effort it would take to do something like this by hand by setting keyframes for each individual blade. To make this look more like the setup from the Starcraft cinematic, I'm going to quickly model a funnel like this and proceed further. I want to create a control rig which will make the setup more convenient for an animator. Here I'm making a NURBS curve and calling it control, CTRL, all in capital letters. And I'm adding some extra attributes, which I will then use to swap into the expression. I'm making a frequency attribute and setting its default value to 1. I'm making amplitude, setting it to 1. And I'm also going to need the offset, and I will set the default to 0, just like in the expression. All of those values are floats. And here I'm also going to be adding a new variable called time. This isn't the same time that is sampled from the timeline. This will be a separate animation curve that the animator will be able to keyframe in order to achieve gradual acceleration and deceleration of animation. And here I'm going back into the expression editor in order to connect control object attributes to the float variables of the noise function. To connect the values, I have to type them like this. First, the name of the control object, which is a CTRL, followed by dot, and then the name of the attribute. CTRL dot amplitude for amplitude, and I'm going to put it in the same order as I have the attributes on the right. Control dot amplitude for frequency. Oh, actually, no, it should be control dot frequency, but I'm just going to change it back in a moment. Offset is control dot offset, and the first one, I'm correcting it right now. Dot frequency. Now it looks correct. And at this point, in order to control different parameters of an animation, I no longer have to go into the expression editor. I can just change the attributes of the control object. And if I remember correctly from the Starcraft 2 cinematic, they had their animation ramp up gradually. I'm going to achieve that by setting amplitude to 0 on the first keyframe, and then a little while later I will ramp it up to 20. If I rewind and play, I will see that the amplitude will increase over time. The frequency, I'm going to tweak it so that the blades move a little bit faster. But in order to increase it over time gradually, I'm not going to put any keyframes on it. This is where the custom time attribute will come in handy. I'm going to put a few keyframes onto the time attribute. It doesn't even matter what they are at this point, because I'm going to be readjusting them later through the graph editor. I put one on frame 1 and second keyframe on frame 60. It's just a random value, and then I'm going to change it anyway. Then I have to go back to the expression editor and add a few lines. The first one will be the float variable for the new time attribute. I will call it float $time. I will put it right next to the offset. This, again, is not to be confused with the time that is generated by the timeline. It's equal to control.time, and it is going to be swapped in for the time that didn't have a $sign in front of it before. So now this is a custom attribute controlling time progression. Next, I'm going to the graph editor for the control object, and I'm going to be changing the slope of the time curve. I want it to start off slowly and over time get faster and faster. I do this by shaping the curve like this. I'm going to view infinity and change post infinity attribute to linear, and you will see that the resulting animation curve will start flat, and then by frame 60 it will achieve its maximum velocity and it will progress infinitely. And at this point, not taking the secondary effects into consideration, we have achieved the mechanical look of the Starcraft 2 cinematic. We have multiple blades that are animated, and the animation that changes over time with just a few lines of code, and control being available through the control object attributes. We can still change them and modify the animation parameters on the fly, either by rearranging keyframes or typing in few values that haven't been keyframed, such as frequency or the offset. Here you can see how we can get all the blades moving in unison simply by zeroing out the offset value. We're practically finished, and let me stop this playback and zoom in on the expression one more time just to show how little effort it takes to produce very complex and random animation. Very few lines of code that are barely different from the original expression that we started with. And having done all this, the question is, can we improve upon this even further? What else can we do with the expression? Well, we can introduce global offsets on top of the individual offsets, and we can control them with built-in object attributes such as translate y of this control object. I'm going to need one more float variable, and I will call it I already used up the offset name, so this one I'm going to call it, how about bend? This will act as a global offset for the entire animation system. I will make it equal to ctrl.translateY. I don't have to make any custom attributes. The built-in one will act just fine. And I will multiply it by 10 so that each point in translation will result in 10 times as many degrees in the offset. And I will put that value at the very end of the expression, right after the amplitude, plus $bend. I will hit edit, and I'm going to move the ring up and down to make sure that its vertical position is affecting the convergence factor of the jet blades. The higher it is, the more towards the center the blades move. And I'm going to put one keyframe at the beginning of the animation. I will shift the circle, put it in a different position, and by frame 60 I will restore it back to where it was originally. If we play this new animation a few times, we will see that the blades will start with no random movement, perfectly converged, and then with the use of our control rig, they will animate as the time progresses. We're practically finished. All that's left now is to save the scene, and I'm going to be providing it in the video description. So if you want to open the file and mess with the parameters, you can load my setup and change the values any way you want. I hope this tutorial wasn't too confusing. If it was, feel free to ask me questions directly through the comments section below this video. I'm going to be making more MEL scripting tutorials covering other uses of the noise function and expanding upon the topic of procedural animation. The objective of this tutorial has been fulfilled. All that's left to say is good luck with your projects, and see you next time!